mind turning on your video. I appreciate it. Thank you. I see there's something in the chat. Let's see. Oh, good morning. Okay, hi. All right, very good. So let's continue. So last time we were talking about an algorithm to test if there's a node hole in a graph. And we said there are 3 steps. And the first step was detecting, well, maybe I'll write something down. So detecting odd holes. And then step 1 was easily detectable configurations. And they were, so we said C5, there's actually, you can hide it into something else. It's not so important. But you have the jewel, which we convinced ourselves, which is this graph. And we convinced ourselves that this cannot occur in a node hole free graph. And it's easy to test for. And then we had the pyramid, which is this kind of graph. And only one path is allowed to have length 1. And we also convinced ourselves that it couldn't occur in a node hole free graph, but you know, it's not obvious how to test for it. And so I told you a theorem that allowed you to test for it, which I'll repeat in a minute. But the first thing I want to do today is show you some of the proof of that theorem. So I'll show you. Let me, so I'm going to erase everything and write the theorem. Sorry about that. And write the theorem in small, in small handwriting on top. And then I'll show you. So the theorem we needed to test for pyramids is the following. Let P be a pyramid in G, and probably, in fact, you maybe have it in your notes, with V of P minimum, and then let F be a frame for P. Now remind you what that is. Let S1, S2, S3, T1, T2, T3 be shortest path somewhere, and I'll say in a minute where. Then F union S1, S2, S3, T1, T2, T3 is a pyramid with V of P vertices. So what does all this mean? It means you take your shortest pyramid P and you look at its frame, which consists of the 3 vertices of the triangle, called B1, B2, B3, the apex, neighbors of the apex, called S1, S2, S3, then the midpoints of the path between the S and the P, called midpoint 1, midpoint 2, midpoint 3. And then the theorem is that if you take any shortest path here, be a little bit careful. Don't let it, you know, go through neighbors and vertices in the frame that you know don't have neighbors there. So take a path like this and a path like that. This was called, I think, S1. This was called T1, and similarly here, and similarly there. Then what you get is another shortest pyramid. All right. So now let's put it. And I'm sorry, I'm going to redraw this again. To draw it bigger. Here is pyramid again. And here is the frame. And I'm going to prove this theorem. Right, so there are 6 paths about which I need to prove it. So I'm going to prove it one path at a time. I'll prove that if I replace one of the 6 paths by a shortest path in the graph, I would be back in, in the situation described in the assumptions of the theorem. I'll get another theorem of size VP, and then I'll replace another path, and I'll say, well, I'm still in the same situation. And so then it's enough to just do it one path at a time. Okay, so let me look at the shortest path. Let's say here is this is the shortest path from S1 to M1, not going through anything suppressed. So, okay, so maybe from this blue path, there are no chords anywhere in these 2 paths. Then I claim there are also no chords to anywhere down here. Because why? Well, I can go, down the blue path and then down those orange chords, and I'll get another pyramid, because we already said there are no chords from this blue to this cycle. But this pyramid is shorter than the pyramid I started with, because blue is at most as long as black, right? Blue is the shortest path in the whole graph from here to there. And then I managed to shortcut through this orange chords. So if there are no chords to this other 2 paths, then there are no chords anywhere. And then that's exactly what I wanted to prove. I could use blue instead of black. So there are chords from blue to this cycle. Okay, let's follow blue starting at M1. So in order to reproduce this theorem, the only thing you need to remember is that you now follow blue from M1 and stop at the first vertex with course to this cycle. If you do it in that direction, it doesn't work. So here I walk, and I found the first vertex with course to this cycle. Now there's 3 cases. Case 1, and remember, it doesn't have neighbors to, it doesn't have chords to any of the red vertices, because I was careful to choose this blue path not to interfere with the frame. Okay, so case 1, this first guy with chords has 2 non-adjacent neighbors in this cycle. Then I claim I can find a shorter pyramid. You go this way, you go this way, and you go that way. So I claim I certainly saved something, because, for example, I'm not using the apex. This is a subpath of the black path. This is a subpath of the black path. And this is a little bit, and this is part of the blue. So you need to be a little careful when you count, because you can say, but here you added an edge, but if you count carefully, it works. Right, and here I'm using 2 things. I'm using the fact that the blue is not longer than the black, so using part of blue is a saving. And also I'm using the fact that there are no edges from this portion to anywhere in that cycle. So, these 3 paths do make a pyramid. That maybe there are chords here, but that's fine. I can just shortcut. That's no problem. Okay, so that's the first case. The second case is when this first vertex with chords has exactly 1 neighbor in this cycle. So then I know it's none of the red vertices, so I can assume it's something like this. I don't really care if it's above this red or below this red. So then I claim I can find a pyramid with this apex. So you basically do the same routine. You go down and around. So now I used all of this cycle, but I think I'm going to save on the other side, because you go and you saved a little bit. At least you saved this vertex, so at least you saved this vertex. So down, around, and this way. And again, I'm using the fact that this area is safe. So last case, this guy has at least, so it doesn't have two non-adjacent neighbors in the cycle, but it has more than just one neighbor in the cycle. That means it has exactly two neighbors in the cycle and they're adjacent. So it's something like this. And now this is the kind of surprising case. So the first thing one might try is to use this new triangle with the original apex. So far it's correct. That's what we're going to do. We're going to use the new triangle as the original apex. But the kind of first impulse is you go down this way, you go around that way, and so far you're safe. And then go down like this. But that's dangerous. You can't do that, right? Because there might be all kinds of courses between this blue bit and this cycle. This portion is safe. This portion is wild. You can't use it. But what you can do is that. Go down black to this midpoint and then come back up. So now maybe this yellow path I've just drawn, is not induced, maybe there's some chords there, but shortcut, that's fine. Right? Within a path you can shortcut, it doesn't cost you anything. You just need to make sure there are no chords between paths. So this green path doesn't have any chords to there, because this is part of the original pyramid and that bit was safe. Now it seems like I've gone an awfully long way, right? I went and then I double backed, but that's exactly where these midpoints are coming in. To go all the way down black and part way through blue is shorter than to go all the way down black and this way, because blue is the same length as that. And I was able to save all of this. All right, so that's the point of taking this midpoint. That's the only reason why a frame needs to have 10 vertices and not 7. That's where the midpoint is. All right. And that's it. So we proved that you can replace this path and it works exactly the same if you try to replace a bottom. Questions? Okay, so we did the pyramids. Now let's move on to the third step algorithm, to the third step of the algorithm, which is called clean shortest odd hole detector. So, and now I can assume there's no pyramid and no jewel because I've already run the first step. Assume no pyramid, no. Okay. So now what we're going to do, we're going to try and find a shortest odd hole in the graph. We're not quite ready to do that yet, but we're ready to do something in that direction. So let me say this is just a definition now. If I look at any hole and I look at the vertex outside, I want to classify vertices as big and small. I remember we had this in the video I showed you from the proof of the strong perfect graph theorem, but we're going to do it again here. So we say V is small if small with respect to its whole C. If the neighborhood of V in C is contained in a two-edge path of C. And V is bigger. So it's clear that every vertex is either big or small. Now, there aren't many small vertices, right? So this is a small vertex, this is a small vertex, this is a small vertex, has two consecutive neighbors. This is a small vertex, has exactly 3 neighbors that make it to edge path. And there's one more. This is a small vertex. Yes, no, yes. These are the only types of small vertices. Every other vertex in the world is big. So it turns out graphs, but holes that don't have big vertices are nicer. So definition, C is clean if no vertex is big for C. Okay. And it turns out that in a graph with no pyramid and no jewel, if you have a shortest odd hole that is clean, then you can detect it using the shortest path detector. So what's the shortest path detector? It means you pick a few important vertices in the hole, you fill the rest with shortest path, you check is that an odd hole. If it is, you output odd hole. If it isn't for every choice of few vertices, then you say there's no odd hole in there. So again, but in order for this to work, I need that there is a hole in this graph which is shortest among all odd holes and clean. Right? It's not the same as saying shortest clean odd hole. That always exists. But I'm saying it's the shortest of all odd holes and it's clean. So here, if G,
could you very briefly repeat again which ones are small and which ones are big in the graph?
Small means its neighbors in the hole are local. Maybe it has no neighbors, maybe it has one neighbor, maybe it has two adjacent, maybe it has three that fall into a 2H path, or maybe it has two, but they still fall into a 2H path. So it goes yes, no, yes. That's small. And everything else is
okay. Okay, thank you.
So, anything else? Okay. So theorem, if G has a shortest odd hole that is clean and no jewel, no pyramid, we can find a shortest clean odd hole in G using a shortest path detector. So what does that mean? What it means is, so there should be some theorem that allows me to use the shortest path detector. This just says it's enough to, there is some algorithm of the form, guess a few vertices and check if shortest path between them make the whole. But I didn't tell you kind of the basis for it here. So what happens is, and I'll draw a picture here and then I'll write it on top because we'll need that too. So what happens is if you have a hole, this is clean shortest, explicitly shortest odd hole, and C is clean. That's why I got lucky. The shortest odd hole in the world is also clean. Then it turns out, if you guess 3 roughly equally spaced vertices in this hole, and you take 3 shortest paths like that, then this blue thing is going to be the shortest odd hole again, and in fact clean. Okay? And just like with prisms, in fact, the theorem is I can, one step at a time, replace black by blue. Okay, so let me write down this theorem that's based on this algorithm. Theorem, I have a graph G, no jewel, no pyramid, and I have a hole C, which is shortest odd. Get a picture here. C is the shortest odd hole in G, and C is clean. And now you take two vertices, U and W and C, that are not directly opposite. So the reason I wanted 3 vertices in my shortest path detector is that I need to make sure the 2 vertices between which I'm going to choose the shortest path are not directly opposite. That's such that the distance in C between U and W is less than half the length of C over 2. Let P be a shortest path of C from U to W. Then finally got to that. 2 things. One, P is a shortest UW path of G. That is not just the shortest in the whole, it's really shortest. And 2, if Q is a shortest UW path of G, then C minus P plus Q is a clean shortest odd hole of lengths the same as C. Right? So this is the theorem. Let me just draw again a picture to explain what it means. I'll just say again what it means. Here's my C, clean shortest odd hole. I look at U and W, which are not directly opposite. I look at any shortest path in the graph between U and W, and the claim is if I use blue instead of black, nothing changed. It's still an odd hole. It has exactly the same length as G, as C, and it's still clean. And in particular, this original UW path of C was in fact a shortest UW path in the graph. Okay. So now we understand 2 of the 3 steps. We understand step 1 and step 3. Right. So just to remind you where we are in the algorithm. So I can detect joules and pyramids. If only I had the clean shortest odd hole, I can detect it. Shortest odd hole. And what's missing is this. How do I arrange that there's a clean shortest odd hole? That is, if there's an odd hole, there's definitely shortest odd hole, but maybe it's not clean, and then then my step 3 doesn't work. So I want to somehow pre-process my graph. I don't know if it's called pre-process if you do it in the middle. I want to process my graph in such a way that if there is an odd hole in my graph, then in the outcome of this processing, there is a graph with a clean shortest hole. Okay? And this is a technique called cleaning. And this is an old technique. It was proposed by Conforti and Rao. Well, I should say proposed. It was invented and used by Conforti and Rao. And I think it was maybe in 1999 or 2000, or a long time ago now. They used it to detect something called balanced matrices, but it doesn't exactly matter what it means. And the idea is the following. So let's say I have, an algorithm that works in some special case, like my algorithm 3. So what I want to do is I want to start with the graph G, and I want to create polynomially many subgraphs of G. So that if G has an odd, so what I have to say, maybe I'll tell you actually what to do here. If G has an odd hole, then one of G1, GK has a clean shortest. Right, so let's just understand what I wrote here because it seems like it's all the same. So I start with some graph, and I want to create polynomial many integral subgraphs, but it's not so important. Any instances here would work, but in our case, it will all be subgraphs. So all I'll do is delete some subsets from G in such a way that if G had an odd hole, then in one of those outputs, I'll be able to use my shortest path. If G has an odd hole, then one of those outputs has a shortest odd hole that's clean. Right. So if only I were able to do that, if only I were able to build such a, such a collection of K graphs, and K is polynomial in N. In our case, actually, it's n to the 7, if you want to know. Then I'd be done. Right. So I do easily detectable configurations. Now I take my G, I convert, I produce n to the 7th graph like this. Now in each of them, I run the shortest path odd hole detector, and I'm done. If there was an odd hole in G, I would find an odd hole in one of those. So the only question is, how do we do that? How do we take G and turn it into polynomially many graphs, one of which is amenable to the shortest path? All right. So in fact, what we will do, we'll say, instead of constructing those G's directly, we'll construct subsets x1 through xk, subsets of V of G, so that for some I, G minus xi has this form. To say, start with a graph and construct polynomially many other graphs is very ambitious. To say start with a graph and find polynomially many subsets of the vertex set to delete sounds a little bit more plausible. All right, is this the idea clear? So now I need to tell you how to construct those subsets. And the key step here is not to erase it here on top, because we constructing x1 through x6. I call them the cleaning sets. Okay, so how on earth would you construct a cleaning set? So here's one idea, and it doesn't work, but at least it gives you some notion of what you might do. Suppose in some magical world that I live in, I could prove that for any odd hole C, or for a shortest odd hole C, there is an edge, so that every major vertex, or every big vertex, major and big is a set of major vertices, big vertices. This is called C1 and C2, and every major vertex has a neighbor in this edge. So every major vertex has adjacent to C1, or to C2, or to both. Suppose somehow I could prove it here like that. Well, then I claim I can construct cleaning sets, because what do? What you would like to do is delete every neighbor of C1 and C2 except those two. And you do it for every edge, so you constructed some number, I don't know, let me say. So you look at every 3 edge pass, and you delete everybody adjacent to the 2 middle vertices, but not those. Those you keep. So how many sets have I constructed? I've constructed n to the 4th, no, at most n to the 4th sets, right? At most, every 4 tuple vertices would give me a possible cleaning set. And I claim this way I managed to clean this hole, because why? When the 4 edge pass that the 4 vertex pass, the 3 edge pass that I constructed is precisely this subpass of this hole, then I got rid of the big vertices because they all were adjacent to this or that, and I left the hole intact. So fantastic. When I got to this particular 3 edge pass, I did my cleaning. That's the GI, that's the XI that works. Okay, so unfortunately, this is not true. You don't necessarily have a cleaning edge like this, but something along those lines is true. And what is true is the following. So I'm going to call this edge M heavy. have a set M, and I have an edge AB, and I say AB is M heavy. If every vertex of M has a neighbor in AB. So it's not true that the set of all big vertices has a heavy edge, but it is true that if I fix any big vertex and I look at all its big non-neighbors, any set like that has a heavy edge. So theorem that V big for C, that M be big set of C heavy vertices non-adjacent to V, then some edge of C is M heavy. Okay, so that's good. That allows me to clean. I can, guess my favorite big vertex, and I can clean every major vertex, all the major vertices are not adjacent, right? So now instead of guessing 4 vertices, I'm going to guess 5 vertices. The major vertex V plus is for each path, and that will do. Okay, so that's a good start. So now I'm still not done because some big vertices are neighbors of my favorite V. But we're making progress. So one thing that's tempting to do is to say, well, delete all neighbors of V. But that's dangerous because you might damage the whole, right? When you're cleaning, you want to delete all the big vertices, but you don't want to delete anything from the whole. So, for example, if you have a major vertex with at most 100 neighbors in the big hole, in the hole, then you're very happy because you can guess this major vertex. You can guess this 100 neighbors that you don't want to touch. You can clean its non-neighbors by what we just discussed, and then you can delete all its neighbors. So that would be nice. So at least now you can assume every major vertex has, a million billion neighbors in the hole. That's sometimes helpful. And now what you do is the following. So let me guess this vertex V whose non-neighbors are clean carefully. I'm going to take, so this is whole C. This is a vertex, I call it V0, major for C. And I want to choose, and I can assume V0 has a billion neighbors in the whole, but probably at least 4 is what I really want. And now we say, choose this, guess this V in such a way that it makes a maximal spread. Now this, if you try to write this down on a piece of paper, it's really hard to explain what it means, a maximal spread. But if I say it to you in words, it's very clear. What I want is that I take this vertex and it makes some sector, and this sector is maximal. Right? So it has it has many neighbors. So like I understand the sector between these two vertices. I understand what it is, this one and not that one, because he has a lot of neighbors. And what I want is the vertex V0, so that there's no vertex that looks like that. So that's all I'm saying. Right? V0 has a maximal sector. So now, what other big vertices are there? Well, there's some that are just like V0. They have the same kind of sector, the same kind of spread. But that's no problem. I can clean them away very easily. Just guess those two vertices and delete all their common neighbors. So now, right, and you're not going to damage the whole. So the other big vertices that are still left are big vertices that have a neighbor in the size 0. They have a billion neighbors somewhere else, but they do all have a neighbor in I0. And they're all neighbors of this V0, which we chose. So, okay, so all I need is to somehow get rid of all these vertices without damaging the whole. Now, what is the size 0? Well, let's go back to the theorem that I so carefully wrote down. I0 is a shortest path between these two guys in some graph. And what graph? In the graph where I deleted all the neighbors of V0. So let's look at the graph. G delete n of V0 union VC, right? I can't find this graph, but I'm not going to find it. I'm just going to apply theorem. So it's a graph where I deleted all the neighbors of V0, but I kept C. I kept all of the whole. So in that graph, this is the shortest path. Let's call this. It ends D1 and D2. Just fine. In this graph, I0 is the shortest path from D1 to D2. So now, well, I can't find this graph, but I can find the graph G minus n of V0. And I claim if I look for the shortest path, I claim I0 is also a shortest path from D1 to D2 in this graph. It's correct. It's a slightly bigger graph. No, it's a slightly smaller graph, so maybe the shortest path got longer, but it didn't get longer because I see that it's still there. You can convince yourself that this is true. Okay, so if only I could compute this particular I0, which is the shortest path from D1 to D2 in this graph, which I can compute, then that would be great, because now I would take everybody with a neighbor in I0 except this and that would get all the big vertices and not damage the whole. Well, okay, I can't compute this particular shortest path from D1 to D2, but I can compute the set of all shortest paths from D1 to D2. So here it is. It's a set of all vertices that are in shortest paths from D1 to D2. It's an exercise to convince yourself that you can do it. So Z is set all vertices that belong to shortest path from D1 to D2 in G minus n of V0. And that's something that's not difficult to compute. So then in particular, I0 is a subset of Z because I0 is some such shortest path. And now let me take X to be all neighbors of V0 with a neighbor in Z. And now I claim I'm done. Because why? So first of all, I definitely got all the big vertices because they all had a neighbor in I0. And now I just need to make sure I didn't by mistake grab anybody from the whole. But remember, I know that any shortest path here can be used in place of I0. Any shortest path that I take here, even in this blue graph, but also therefore in the green graph, will not have any course to them. That's statement 2 of the theorem on top. So that means that is completely safe. I'm not going to damage the whole. There are no edges from this part of the whole to those paths. And I've managed to collect all the big vertices. All right, and that's how cleaning works. And you can convince yourself that you have to guess. And so I say, guess this, guess that. That means go through all possible subsets of certain properties, and you can convince yourself that the subsets I go through all have size most 10 to the 7th. All right, so this was that. Questions? And by the way, if you sort of care about this algorithm, the strong perfect graph theorem, I don't recommend that you read the paper. Like, if you want to understand some parts, you could read the paper, but otherwise it's not a good idea. But this is a 15-page paper or something like this. You can read very easily. Really, I told you the whole proof, and it's all written down. It's much easier somehow. Okay, I'm going to erase the board and I'm going to switch to something completely different.
Dr. Chernavsky, could you, so the second part of the algorithm, the cleaning part, that's basically finding a bunch of subgraphs of G, and one of them needs to have an out hole.
Clean shortest hole.
A clean out is, okay. And could you, and since there is n to the 7 of these subgraphs, would it take n to the 7 time to calculate them, or I'm guessing maybe it takes more.
Well, it's 10 to the 7 subsets, but then you need to do something to them. And that's why you need 10 to the 9. And again, there's some work that brings it down to 8 to the 8 to n to the 8.5.
Okay, thank you. Yeah.
That's helpful. Okay. Okay. So we're moving on to Cloffery graphs.
One quick question. So are we saying that computing Zi can be done in n squared time, like computing all the?
Yeah, I mean, so this is a tough question. I can never answer questions like that. In this last step, so you guess V0 and D1 and D2, and then you could compute all the vertices that are in shortest path from D1 to D2, which probably takes 10 bot n cubed, I think. And then you take everybody with a neighbor in that set that you got. So that particular step, I mean, somehow, like, you don't need to go through all 7 tuples and then do everything to them. They can do some things to some triples, right? So you have these triples from the last step, Z0, D1, D2. And you also have 4 tuples from the first step when you clean out the non-neighbors of D.
So
these are the 7, the n to the 7th. It's 4 tuples and the triples. But you do different things to the triples and the 4 tuples. So you don't need to do everything to every 7 tuple.
I see. I understand. Okay. Thank you.
I mean, I won't be able to give you an honest complexity analysis.
Okay. Thank you.
It's somewhere in there, the 10 to the 9th, even though if you do it, completely straightforward, in a straightforward way, it's probably a little bit more than that. Okay?
Thank you.
Okay. So now we're moving on to Cloffery graphs. And the thing about Cloffery graphs, I'm going to tell you about generalized line graphs. I'm very excited. I'm finally going to tell you about generalized line graphs. So what are Cloffery graphs? So a claw is this, and G is Cloffery if no unused subgraph of G is K13, or it's a claw. And they're kind of popular. So first of all, they're generally thought of as a generalization of line graphs. Fact, which you can amuse yourselves by trying to prove. Line graphs are Cloffery. And this is really easy. Just try the obvious thing and just. And traditionally, I think Cloffery graphs are sort of generalizations of line graphs in the sense that there are all kinds of algorithmic problems that you can solve in line graphs, and then sometime later somebody solves them in Cloffery graphs. Probably the most well known is max matching. That's for the time, and that's a theorem of Edmonds. And then you can say it just in a different language. And let's say it's max weight, which is fun. And in a different language, you can say max weight independent set in line graph. So that's the same problem, that's the ordinance. And then you can move on to max weight independent set in Cloffery graph. Right, so that's now a different problem because in fact not all Cloffery graphs are line graphs. But you can still solve it, and it's an algorithm of Minty. I think it was Vatalensbichi. If you don't say maximum weight, you just say maximum size. But then Minty did it for the weight. Okay, and there are some things about their stable set polytopes. So somehow, I don't know, people think of, especially people in optimization think that Cloffer graphs are an important class of graphs. They're somehow right there on the border. Nothing is trivial, but many things are true. So you like that. So, and then Paul Simmer and I started thinking about their structure. Originally, we were trying to just understand the perfect Cloffer graphs. But then after we got that theorem, we realized that our techniques were not really so specific to perfect graphs. So it just happened to be solving that problem. And then 3 years later, we could do the general problem. Okay, so first of all, let me convince you that Cloffer graphs are not line graphs. And the way I'll try to convince you of that. So in a line graph, this is H and this is the line graph of H. So here I have edges, here I have vertices, right? So an edge here, it has edges that share this end with it, edges that share that end with it, and maybe parallel edges. F. So in the line graph, this vertex that corresponds to F. So let's call those X, those Y, and those Z. So it will have neighbors that come from X. It will have neighbors that come from Y. It will have neighbors that come from Z. But notice X union Z is a clique. Every edge in X, every two edges in X share an end. This one, and they all share an end with Z. So this is a clique. And also Z union Y is a clique. So if I look at a line graph, for every vertex, its neighborhood is the union of two cliques. And I guess I proved the theorem that I told you to think about. In a line graph, for every V, N of V is the union of two cliques. And graphs like that have a name. They're called quasi-line graphs. So quasi-line graph means this. So they're Cloffer graphs, they're graphs with these properties which are called quasi-line graphs, and they're line graphs. And I claim these are all three different things. These. Okay, so let me show you that. So first of all, let me construct a Cloffer graph which is not a quasi-line graph. And this is a construction that some people might know from geometry. It's called the Schläfli graph. So the Schläfli graph is the following. Schläfli was German, so possibly it's the Schläfli. So you start with the line graph of K33. The line graph of K33 is 3 rows of triangles joined together by 3 columns of triangles. And you draw it 3 times. So now, you start with the three copies of the line graph of K33. Now I'm going to tell you the edges between. So the rule is between these 2 copies, it's columns to columns, right? Every column here picks some columns there and becomes adjacent. And the column here is complete to some columns there. So in this pattern, the first column is complete to those 2, this one is complete to these 2, this one is complete to this 2. So just to make sure we understand what this picture is. So these 3 vertices don't have any neighbors among those 3, but they're complete to this 6. Okay? And I've tried to draw it symmetrically, like this column, it's anti-complete to that and complete to everything else. this column is complete to this and that, and anti-complete to that. Okay, so that's between these two. This one is complete to this. So now between these two copies, it's the same story but with rows. The first row is doing this, the middle row is doing that, the third row is doing this. And between the side copy and the top copy, it's his columns to his rows. So like this. This column is complete to this row and that row, and anti-complete to this row. And you know, if you really care, you can look up shape. Okay, so you can convince yourself that this is a Cloffery graph. And it's not a quasi-line graph because it's very easy to see it has subgraphs like this. So let's see if I can spot one quickly. So it's very easy to see, but of course, hard. Maybe if I go 1, 2, 3, 4, and then this is going to be 5. So it's going to be this guy. And now I just need to find the correct person there. So here, people that are adjacent to 1 and 4 and not 2 and 3, they live here. They live in this row, and I want it to be adjacent to 5. So this one is. Okay. All right. So so this is we just plotted the guide here. Okay. So now let's get. So this is neat graph. But, now let's get somebody in this area, somebody who is a quasi-line graph, but not a line graph. And now we're going to actually construct a very important infinite family. You know, Paul Simon and I were working on this problem, and somehow we had a lot of trouble with the Schläfli graph. And we're going to write a theorem that says, to write a paper that says every Cloffery graph is either this or this or this or that, or has at most 27 vertices. And it was kind of frustrating because, from a very explicit construction, suddenly it's just a theorem about big graphs. And then we talked to Adrian Bondi, who some of you may know, may have heard of, and we complained about our bitter luck. And he said, but this is a Schläfli graph. And we said, oh, okay. And so that's how it ended. Okay, so now let's get one here. So one here, I'm going to call them, I'm going to construct the family of circular interval graphs. So some of you might know about, some of you might know about circular interval graphs, but probably all of you know about circular arc graphs, but that's different. The circular interval is not the same as circular arc. So circular interval is the following. You start with a circle and some intervals. And then, so far it's like in the circular arc graph. Now in circular arc graph, you just take, the intersection graph of the interval. But now I'm going to do something else. Now my vertex set is going to be a subset of the circle. Say like this. So the orange guys are subsets of the circle. So I have a circle called sigma. I have V subset of sigma. And then I have a collection of intervals I1 through I2. And what I need to tell you now is the adjacency between the vertices. And the rule is two vertices are adjacent if one of the intervals contains them both. X, X, Y is the mu of G if there exists I, so that X and Y are both, J maybe, are both in IG. Okay, so that's a rule. Now I told you how to construct the graph. Let's just finish this example. So those three are a triangle because they all belong to this interval. These two are adjacent because they both belong to this interval. These two are adjacent because they both belong to that interval. These two are adjacent because they both belong to this interval. These three are adjacent. So let's make it really interesting. These three are adjacent because they belong to this interval. And you could make it more interesting than that. This interval, and then that would tell me that actually those four are clique. Right? So that's a circle interval graph. And you can check that it's a quasi-line graph because for every vertex you look at its clockwise neighbors and its anti-clockwise neighbors. And there's an interval that contains all the clockwise guys, and there's an interval that contains all the anti-clockwise guys. And you can check that it's not a line graph, and that's harder. It's some paper somewhere, but you can do it. Okay, so this is really a knowledge hierarchy. And what I'll do next time, I'll tell you about the structure of quasi-line graphs, and then I'll tell you the structure of all Lofty graphs is like this, but much harder. And maybe this is enough. Thank you. I'll see you Friday.
So, thank you very much.
Sure. Let's see what's in the chat. Okay, so tell me what. Okay. All right. Again, thank you for people who are answering questions. Okay, so I think all the questions in the chat are no longer. There's the new one. Circle interval graphs are not perfect because, for example, so somebody said, are circle interval graphs perfect? And they're not because you can represent C5 as a circle interval graph. I just think. Take this circle and take those intervals and take these vertices, and the graph you get from this picture is precisely that, which is C5. Anything else? All right, so then, thank you very much.